Hi, my name is Caroline Flagler and I'm doing the Chem 205 Orgo exam. This was initially blank, but it's my third time recording, so things are already filled out now. But I will just go ahead and jump on in. The hardest thing I found that I'm having trouble with is the camera, so the camera might not be perfect. So right here, number one, perfect. Okay. So with number one, you can obviously tell these are resonance structures. And what I found is the most helpful way to understand a resonance structure is that they're two Lewis structures and they have the same placement of atoms, but they're going to be in a different arrangement of electrons. The double-headed arrow simply shows that it's used to separate the two resonance structures. The curved arrow is what shows the movement of the electron pair, and the head of the arrow right there is where the electron pair moves to. And then let's see, the two electron pairs move in each structure. That's really all you need to know about number one, and that the lone pair forms a double bonded methane, which is the C connected to four H's. And as long as you follow the no more than four bond rule, so where a carbon's attached to four atoms because it obviously can't take on five alone. That's all I think you would really need to understand number one. So this is my structure one more time. Moving on to number two. I think I'm going to hold it up for a moment and then explain it and then hold it back up after. So I think the most helpful thing to understand with number two is simply definitions. So I think the main definitions that one would need to know are like the Lewis base, Lewis acid, the Bronsted-Lowry base, which from now on I'll just call it Bl, the Bl acid, and then the Bl acid base reaction. So really what needs to be known about this is that a Lewis base is an electron pair donor, and the Lewis acid is an electron pair acceptor. I'm going to go ahead and put this down for a second so I can explain. And then the Bl base is a proton acceptor, and it has to be able to form a bond to a proton by donating the electron pair. And then the Bl acid has to have a proton donor, and it must contain a hydrogen atom, which is easily seen in this acid. And then with the acid, the first one, you know it is because it contains an OH bond, and that's one of the big signifiers that makes this an acid. And you always know that if you first have an acid, the first portion of your final product, again, sorry, I'm having a really hard time with this camera. The first part of your final product is going to be a conjugate base. And then that, let's see what else. Oh, and then just overall understanding what a Bl acid base reaction is it's always resulting in a transfer of a proton from an acid to a base, which is clearly shown in the first step of the curved arrows right here. So just again, holding number two up for a second. And then moving on to number three. Again, this was once blank, but with a third attempt, I had to go ahead and write down everything. So over here in number three, this is your aromatic ring, and you know it's aromatic because of its phenol group, and it's bonded to six-membered cyclohexane ring. The other two groups that are right next to it are amides, and amides with this one, you know it is because of the CONH2, but two other ones that would be noticeable are the CONHR and then the CONR2. Sulfide is right up here. This is its general structure. Two R's bonded to the S with two electron pairs, and it's an SR alkyl Theo group. The final functional group was the easiest one to spot. It's the carboxylic acid, and you know it is because of the COOH, which allows it to be the carboxy group. And there are two methyls listed right here, but in our textbook, they weren't considered functional groups. So I just wrote it down as methyl, but I didn't circle it. And number 4, I went ahead and added an asterisk on the 6 chiral centers. And with chirality, I think what you'll really want to understand is that a chirality center is the carbon atom bonded to 4 different groups. And then with no stereogenic centers, a molecule usually isn't chiral. With only one tetrahedral stereogenic center, a molecule usually isn't chiral either. And lastly, with only 2 or more stereogenic centers, a molecule may or may not be chiral. So I think those are the key things to remember. I'll hold number 4 up one more time. And then moving over to number 5, I drew the chair conformation of the cyclohexane. And I think with number 5, what you'll really want to understand is the difference between axial and equatorial. So axial hydrogens are located above and below the ring in a perpendicular axis. That's how you see the H's will normally be straight up and down. And then the equatorial hydrogens are located in the plane of the ring. So that's going to be more of the diagonal approach. And then I drew my conformation in its equatorial state because that is considered the most stable state. And then, another thing about the planar cyclohexane ring is that you would experience angle strain because the internal bond angles between the carbons would be 120 degrees, shown right here in my circular portion. And then, an angle strain is simply that the tetrahedral bond angles would form an angle of 109.5. And that's all that I had to say. Oh, and then cis, an easy way to remember that is cis, same side. Yeah, so going on to number 6. I thought number 6, again with this camera, sorry. I thought number 6 was the trickiest one. You do understand it's an elimination reaction, but I believe since there are 2 substituents removed from the molecule, and it's a 2-step mechanism, it would be E2. Just showing this again. Because the Lehman group comes off creating a carbocation when a base and the proton from the carbon, the pi bond forms. Yeah, which is C right here in the final step. That's the pi bond. Okay, I'll show it one more time and then I'm going to move on to the last page. Okay, number 7 right there. Okay, so with number 7, initially I drew the circle because it's the most accurate representation of the ring. So the electrons that form the double bonds in the Lewis dot structure are delocalized, which is the same in its resonance structure. This is simply showing delocalization. So since there's 6 electrons that form, 3 double bonds, which are delocalized, are the more accurate drawn circle representation, which shows all of the places the bonds would be. So that's why I drew the circle. With this one, I think all that's really important to know is that the nu, which is the methyl group, it can go from either side, which I've drawn right here. The chlorine is the leaving group, and with the loss of the chlorine, it creates a trigonal planar carbocation. And I immediately knew this was substitution based on the reaction, because the reaction is where an atom or atom groups is replaced by another atom or atom group. And another key thing to remember with substitution is that with one sigma bond breaks, another is formed at the same atom. So that was really a key factor for me. And then I guess the last thing is just, again, brushing up on the Bl acid-base reaction. You know that the base reaction always results in the transfer. Well, the Bl acid base reaction is always going to result in the transfer of the proton from an atom to a base. So with that being said, you know that this is going to lead to a neutral product. So again, that's just emphasizing that it's going to be losing its proton. So I wrote that this is a substitution product, and you also know that it's SN1 because the rate determining step is unimolecular. I thought that was the key factor here. Moving on to number 8A, I went ahead and drew the enantiomer of the given compound. Let me try to get this going again. And enantiomers are mirror images that are not superimposable. And with these two images, you know that they are mirror images and not superimposable. So you know that these are going to be stereoisomers. When it's rotated, the plane polarizes light in the opposite direction. So that's simply emphasizing S and R. So once again, this is 8A. The last one, 8B for the IUPAC name. The first thing you're going to want to do, here I have my pencil, is count your longest chain. So you're going to start from the very beginning and count 1, 2, 3, 4, 5, 6, 7, 8. So in this case, you actually just go straight across. So we all know from memorization that 8 is octane. So that's the first part you're going to write down. Then you're going to want to look at your groups. You can tell on number 6, for memorization, that's an ethyl. And then with number 3, you know that this is going to allow the halogen to change from the chlorine to the chloro. So your overall name, not including the S or R, is 3-chloro-6-ethyl octane. So I'm covering up the letter at the moment, but this is the name. And then to figure out if it's an S isomer in S configuration, you're going to want to assign the priority to each group from highest to lowest, and then the ones that are bonded to the stereogenic center. So easily what you know is that the hydrogen is going to be the lowest group, and then the chlorine is going to be the highest priority. So then you label that, and then you already can tell with a general understanding that the ethyl group is going to be the second to last for the lowest priority. So from there, that is all you really need to know. Yeah, so if you understand that your chlorine is the first, and then second, third, fourth, you're just going to draw in the counterclockwise circle, and boom, that would lead you with your S. And that's all for my final exam. Thank you so much for your time.